about this is it's a graph that we're kind of unfamiliar with. So here we see the percent of dry weight of different plant sources during like their growing season. And then here we have the months. But for each month, we have like 4 tick marks. So this would be like the first week of May, second week of May, third week of May, the fourth week of May. So this would be like the first day of June right here. So that's a little difficult to look at the axes. So this graph are plants that live less than 1 year. So they're annual plants. They only have 1 year of life. We're identifying the direct source of energy used for plant growth during the first week of May and identifying the part of the plant that grew the most during this period. So during this first week of May is this area right here. So, do you see here where it says germination? That's when you have the seed that imbibes water and then it starts to grow. So, where is the plant getting most of its nutrients from? Not the soil, not water, not sunlight. No. No. So, I can take a seed, right, and I can put it in a glass of water and walk away, and put it in a dark room and walk away and do nothing. And it'll start to germinate. But where's the source of energy coming from? Remember, this is, where's the glucose found, though? Okay. Okay, so here's the dirt. Here's the seed that's underneath the dirt. There's no photosynthesis happening here at all, right? Because there's no sunlight getting to that plant. And we're not getting energy from soil or the dirt. Because I have a lot of like plants in my house. I go around and I might give them fertilizer or water, but I never go around with a bag of dirt and add more dirt to my plants. Like, you guys have never seen your moms like go around and add dirt to your house plants. So plants don't get energy from dirt. They don't get their biomass from dirt. Like, I never have to go and like replace more dirt. So they do need to carry out, though, it can't do photosynthesis, so it's going to need to do some cellular respiration. But where is it going? It's not going to get its energy from the dirt. It's not going to get it from the sun. But it's going to get it from the stored sugars or starches or nutrients that are in the seed. Yeah, each seed has like nutrients in it already, like stored sugars and starches and things like that. Well, what animals have that are different than plants, like a chicken egg. Like in the H building, all those freshmen are playing with baby chickens right now. And those baby chickens, like there's a yolk and there's a white in the egg, right? So the yolk is where like the egg cell is, and when the sperm fertilizes it, this is where the growing like chicken is, and all of that white is food for the baby. Like there's stored nutrients in there for the chicken as it grows until it hatches out of its egg. So the seed has stored nutrients too. So are we good on this so far? The one thing that I do want you guys to know, like this is photosynthesis. Okay, this is photosynthesis. Water is a source of electrons, and that's why we need water for plants, because they need electrons to keep photosynthesis happening. It's the only reason we need it for. Because see, this is waste. Oxygen is waste for a plant. So these oxygens are leaving, as waste, and the hydrogens are just providing electrons for the photosystems. The carbon right here is where we get biomass from in plants. So if a plant gains mass, it's getting it from carbon dioxide from the atmosphere. So we have a source of electrons, we have our biomass, but the energy that plants get is from sunlight. It's not in the chemical equation because it's not matter, it's energy. And then the plants use it to create organic molecules. Here we have glucose, and then oxygen leaves as waste. This is stored chemical energy for the plant to either grow or to store for later on. So, we know that the energy that plants get when they germinate as seeds, it comes from, it's stored energy in the seed. Identify the part of the plant that grew the most during this time period, and this little shaded area is roots, and most of this right here is shaded like the root, so that's the part of the plant that grew the most during early germination is the roots. So far so good with A? I can't hear you, hon. They don't give half credit. No half credit. All right, so then, based on the data in the graph, estimate the percent of total energy that the plant has allocated to the growth of leaves on the first day of July. Here's the first day of July right here. And leaves go from here to about here on the first day of July. So this goes up to 100%. So we're going from something that's around 50 to 100. So the amount of energy that went to the allocation of leaves is about 50%. If you wrote anything between like 45 and 55, that's fine and in the rubric. Here's where we start to talk about natural selection. Compared with perennials, plants that live more than 2 years, annual plants often allocate a much greater percentage of their total energy to growth of reproduction parts in any year. Propose one evolutionary advantage of that energy allocation to annual plants compared to perennials. Ben? No. No. How long do annual plants live for? 1 year. Perennial plants can live up to 2 years. Why would annual plants take more energy to their reproductive parts in a year compared to perennials? Yeah, so they can reproduce. They have 1 year to reproduce. Perennials have at least 2, if not more. So, if you only have 1 year to reproduce, that advantage to putting more energy into reproduction would increase your chances of reproducing before you die. If you knew you only had like 1 year to live, you would want to make sure that you would reproduce in that year. And if you don't use that strategy to put a lot of investment into reproduction, then that species is going to go extinct. You have to reproduce in order for the population to be sustainable. Okay. Let's look at this last one that I gave you today before you guys go. All right, what are some things that you just notice by looking at the bar graphs? Yeah, there's no significant difference in time 0 or in 1 hour with or without exercise? I think everything overlaps with everything else, doesn't it? So nothing in this experiment is a significant change. So, they want to look at the release of prolactin in blood. They measured the concentration at 0 and 1 hours after exercise. And then we also have a control group. They want to justify the use of without exercise treatment in the study design. So why would it be good to have a without exercise treatment? I'm sorry? A way to compare results. So then if there were changes in the exercise group, we could attribute those changes to exercise only. We need to have a control group for comparison. That also allows you to rule out normal fluctuations of prolactin that are not based on exercise. And in B, using evidence from specific treatments, determine whether prolactin release changes after exercise and justify your reasoning. Does not affect release. Your justification has to talk about these error bars. And you can talk about the error bars overlapping. And because they're overlapping, that shows that there's not a significant difference in the standard deviation of the means. So stating what the error bars are, standard error of the means, so there's no difference in the standard error of the means because of the error bars overlapping, then there's no justification that exercise affects prolactin. Okay. So, who's coming tomorrow? Anybody? What do you guys want to do tomorrow? Neurons like action potentials, like the sodium potassium pumps and ion channels and all of that? Okay. So neurons and neural signaling. Okay. What else do you guys want to talk about tomorrow? Immunology again? Okay. Watch it not be on the exam at all, too. Like, seriously, like, it could show up and be a ton, or it could be not on there at all. Have you guys taken any of the multiple choice questions? Is it more about osmosis?
Yeah.
How about calculating like osmotic potential and things like that? Remember this? The solute potential equals a negative C RT. That one? That? All right. Let's talk about like how things get in and out of the cell and osmosis. So we'll do like cell transport and stuff like that. Signal transduction pathways? Yeah. Reception, transduction, response. Hormonal signaling, we're okay with those. But some hormones are not steroid hormones. Like, yeah. Okay. Any of you guys at 1 coming tomorrow? Seema, any of you guys coming tomorrow? Okay. Anything that you want me to talk about if I put on a video? You guys look like you're feeling pretty good. Yes. Okay. So that is definitely like on our list. Also, like if you want, like Bozeman has a nice video on that too. Okay. So, what I think you guys should do too is I have all of those multiple choice questions that are open on Mastery Manager. You might want to just take some of those and see what questions you get right and wrong. And then if you get questions that are wrong and you don't understand why they're wrong, we can talk about those multiple choice questions as well. Okay? And then tomorrow, if you come, we can look at your old FRQs from the old exams too, and stuff like that.